So as we start a new chapter, which is all about quadratic equations and parabolas, I've already attached, following this little short video, the previous video about why parabolas are shaped the way they are, why quadratic equations make that U shape. So you can watch the video. It's about 6 minutes and 20 seconds long. And if you don't want to watch the video, you can go ahead and fast forward to the 6:45 mark, and we'll pick up from this screen. Before we get to the shortcuts for graphing functions that are not linear, I want to talk about the quadratic function. So a quadratic function is a function that's in the form of y equals x squared. It's a function with an exponent of 2. So that exponent of 2 is what makes it a quadratic function. So I want to explore with what a quadratic function looks like with a t-chart. So over on the left here, I've got y equals x squared, and we're going to plug all those numbers in for x, which just simply means we're squaring each one of those numbers. So 3 to the second power of 3 squared is 9, 2 squared is 4, 1 squared is 1, 0 squared is 0, negative 1 squared, so that means negative 1 times negative 1, and that's actually positive 1. So negative 2 squared is positive 4, and negative 3 squared is positive 9. And then I graph each one of those. So 3, 9 would be to the right 3 and up 9. That places it here. 2, 4, 1, 1, 0, 0, negative 1, 1, negative 2, 4, and negative 3, 9. So when you draw this shape, it actually makes a U shape with a rounded bottom. So I'll draw the best U that I can. It's not a sharp corner in the bottom like the absolute value function that was the V shape. It should be a rounded bottom. And the reason it's a rounded bottom is because what is going on with all those little tiny fractions and decimals between negative 1 and positive 1. Say, for example, that I were to use 1/2 as one of my points in a t-chart. 1/2 squared is 1/4, because 1/2 times 1/2 is 1/4. So you would have to go over a half, but only up 1/4 of a unit, which would place it about right there. It's not like with the absolute value function. The absolute value of a half is a half, and it would be in a straight line between the 1 and the 0 here, and the 1 be a straight line, which is why it's not a sharp corner down there, and that's why it's a rounded rounded vertex at the bottom of that U shape. The domain, it is all real numbers. And the range, notice that it goes only down to 0, and then everything else is above it, so it'd be y greater than or equal to 0. Graphing a quadratic function is usually a little more difficult than graphing your absolute value functions because of the location of these other points. Because notice the higher we go up, the farther these points get from each other. So what is a quick way to get those points located? And the answer to that revolves around the pattern that is created by the numbers in those points. So down here I have 0, 1, 4, 9, 16. What is the way to describe that pattern? Let's say back we were in geometry or in Algebra 1 or even in junior high math, and the question was, what is the next term in the sequence? How would you describe the pattern, and then what would be the next term of the sequence? There's actually two ways to describe that pattern. One way that many students remember is that they see that I'm adding the next odd number between each terms in the sequence. So 0 plus 1 is 1. And then 1 plus 3, that's the next odd number, is 4. So 4 plus 5 is 9. And then 9 plus 7 is 16. So I'm adding the next highest odd number. But there's actually another way to describe that pattern. It's because 0, 1, 4, 9, 16 are all perfect squares. 0 is the same as 0 squared. 1 equals 1 squared. 4 is 2 squared. 9 is 3 squared, and 16 is 4 squared. So no matter what pattern we follow, we're going to come up with the same number. So the next term in the sequence would be 5 squared which would be 25. And that also follows adding the next highest odd number, which would be 9, to 16, which would be 25. So either way to describe the pattern works. So knowing that, we can come across a quick and easy rule to figure out where the next points are located. This is not a rule that you're going to find in any textbook. You're going to find it probably on the internet, obviously finding it in this video. So I simply just call it the 1, 3, 5 rule. What the 1, 3, 5 rule is, and it's not rules, it's rule. There we go. The 1, 3, 5 rule. What the 1, 3, 5 rule is that starting at the bottom of the graph, starting at the vertex, I can find my next set of points by going out 1 and then up 1 unit. So out 1 and then up 1 unit on both sides. And then I can, from that point, I can go out 1 and then up 3 units. So plus 3, and then out 1 and up 3 units. And then from these points, I could go out 1 and up 5 units. 1, 2, 3, 4, 5. And out 1, 1, 2, 3, 4, 5, plus 5. So that's why it's just simply called the 1, 3, 5 rule. It works. The proof is down there, how the next highest odd number is related to perfect squares. And so feel free to apply that when you're graphing these U-shapes. Okay. So consider f of x equals x squared plus 4x minus 3. We prior did t-charts on how to do quadratic equations, and this is a quadratic equation because notice it does have the highest exponent of 2 right there. So let's just show using a t-chart that this really is a quadratic equation, and also see some of the issues that you would run into if you chose to do everything with t-charts. So we're going to do a t-chart. And let's just use 2, 1, 0, negative 1, and negative 2 on our t-chart. So what that means is we would have 2 squared plus 4 times 2, and then minus 3. So 2 squared is 4. 4 times 2 is 8. And minus 3, 4 plus 8 minus 3 is 9. So the first point would be located at 2, 9. And then we do the rest of them. So we can do negative or positive 1. So that would be 1 squared and 4 times 1. So 1 squared is 1. 4 times 1 is 4. Minus 3. 1 plus 4 minus 3 is 2. And now we'll do it with the zeros. So that would be 0 squared plus 4 times 0 minus 3. So that's just 0 plus 0 minus 3, which is negative 3. And now do it with negative 1. So that's going to be negative 1 squared. So what is negative 1 squared? Negative 1 squared would be positive 1. 4 times negative 1 is negative 4 minus 3. So 1 minus 4 is negative 3. Minus 3 is negative 6. And then we can do it with negative 2. So negative 2 squared is positive 4. 4 times negative 2 is negative 8. Minus 3. 4 minus 8 is negative 4 minus 3, and that's negative 7. So let's graph those and see what we have so far. So we have 2, 9, 1, 2, 0, negative 3, 1, negative 6, and negative 2, negative 7. And I don't know about you, but that sure doesn't look like a parabola to me. And that's one of the problems with trying to do everything with t-charts, is that sometimes you don't get the actual shape of the graph because we're not picking the right number. Maybe the vertex or the turning point is far away from 2, 1, 0, negative 1, negative 2. So we're going to have to pick some other points to figure out where the turning point is, and I'm going to say it's probably further to the negative. So let's do negative 3 and negative 4 in our t-chart as well. So when I plug in negative 3 in my t-chart, so I'll have negative 3 squared plus 4 times negative 3 minus 3. So negative 3 squared is positive 9, minus 12 minus 3. 9 minus 12 is negative 3, minus 3 would be negative 6. And then once more with negative 4. So negative 4 squared plus 4 times negative 4 minus 3. So negative 4 squared is 16 minus 16 minus 3, which is just negative 3. So negative 3, negative 6 puts it right here. And negative 4, negative 3 places it right here. So that looks like that's where our turning point was down here at this very bottom point. So I'll go ahead and graph it with a U shape, rounded bottom. And it's about more like this, actually. So roughly like this. Here is a much more accurate representation of the graph using Desmos at desmos.com. This is a graphing utility that we're going to use later on in this class. But you can see that it does make that perfect U shape with a vertex down here at the bottom located at negative 2, negative 7, just as we saw on our handmade graph. Right there. So that did take a while, but what we were going to focus on is we want to learn the shortcuts to graphing and that we don't run into problems like we just ran into where the points that we picked from 2 to negative 2 did not work very well and we had to pick extra points. So some key concepts here regarding graphing. So this, it says, consider the graph of y equals x squared plus bx plus c where a does not equal 0. This was referred to as standard form of a parabola or standard form of a quadratic equation. There are going to be numbers in the a, b, and c positions. So it looks like there's a lot of variables there, but there will be numbers in the a, b, and c positions. First off, the y-intercept of the graph is located at the c value. The y-intercept of the graph is located at the c value. So thinking about how it relates to slope-intercept form, where the y-intercept was the b value, which is the last number in y equals mx plus b. The y-intercept is going to be the c value since there's going to be more numbers, but it's still the last number in that standard form. This is probably the most important part of the concepts, is that the equation of the axis of symmetry is x equals negative b over 2a, and the x-coordinate of the vertex is x equals negative b over 2a. These are two very important formulas that you're going to use quite often when dealing with quadratic formulas, quadratic equations, and graphing quadratic equations is negative b over 2a. And then the last thing, and I wrote this in because they didn't write it into the book, it deals with the a value. The a value determines the stretch, compression, and possible reflection. Every one of these numbers are in the a, b, and c position is going to have some value to it. So the c is definitely the y-intercept. You can see that we use both a and b in trying to define the vertex, and we also use the a to determine the stretch or compression. Remember, stretch or compression means that a stretched graph is tall and skinny, a compressed graph is short and fat, and a reflection means it may turn upside down instead of the right side up U shape.